Hello viewers, welcome to the session on Single Arm Bandit in Machine Learning. Please make sure to watch all the prerequisite videos for your clear understanding and to make best use of it. So what is this Single Arm Bandit? I'm pretty much sure that you all have come across this machine, in which you have to pull the level once and randomly it pops out the machine's images. And if all the three images are same, then it's your lucky jackpot. So, single arm bandit problem is purely a probabilistic problem. Let's consider an example where we are having 5 similar kind of single arm bandit machines. And our task will be, as a data scientist, to predict the best machine out of the 5 where we can get the maximum number of jackpots for a fixed number of trials. And it's definitely a random problem and its result will also change randomly. So now let's look at the definition of single arm bandit. The one arm bandit is a slang term for slot machines. And although the chances are slim, we know that spinning the one arm bandit has a probability of winning. This means given enough trials, we will win at some point. We just don't know the probability distribution and can't discover it with a limited number of trials. Now let's understand the multi-arm bandit problem. In a probability theorem, the multi-arm bandit problem, sometimes also called as K-1 or N-arm bandit problem, is a problem in which a fixed limited set of resources must be allocated between competing choices in such a way that it maximizes their expected gain, when each choice's properties are only partly known at the time of allocation and may become better understood as time passes or by allocating resources to the choice. So this is a classic reinforcement learning problem that exemplifies the exploration and exploitation trade-off dilemma. The name comes from imagining a gambler at a row of slot machines, sometimes known as one-arm bandits, who has to decide which machine to play and how many times to play each machine and in which order to play them, and whether to continue with the current machine or try a different machine. So, the multi-arm bandit problem also falls into the broad category of stochastic learning, scheduling. So, we have come across the terms like exploration and exploitation. So, what is the difference between them? It's just simple. When we come to exploration, it means that improving knowledge for long-term benefit, whereas in exploitation means exploiting the knowledge for short-term benefit. Now let's look at the applications of bandit problem. There are many practical applications of bandit model. For example, in clinical trials, investigating the effects of different experimental treatments while minimizing the patient losses. Second one, finding the adaptive routing efforts for minimizing delays in a network and also designing a financial portfolio and moreover, and in ads industry. Let us suppose in a website 5 ads are popped up. Now we can recommend the organization that out of these ads, which is that particular ad the user is clicking the most. Now let's suppose that we are given the normal distribution of all the 5 ads and the ad agency want to find out which ad is going to give them more profit, because the more number of clicks, the more number of profit they are going to get. But to understand this, you need to understand upper confidence bound. So don't worry, we will come back to this slide again. For understanding that, we need to understand what is upper confidence bound. Before that, what is one-sided bound? There are 2 types of bounds. One is two-sided bound and another one is one-sided bound. So a one-sided bound defines the point where a certain percentage of population is either higher or lower than the defined point. This means that there are 2 types of one-sided bound, that is upper-sided bound or lower-sided bound. Upper confidence bound or lower-sided bound. So this is just the visualization of what we have just learned, that is two-sided bounds and lower one-sided and upper one-sided. Here it represents that 90% of the population is greater than this 5% of the population, and it is lower than this 5% of the population. Similarly, for the lower one-sided bound, it states that 90% of this population is having value greater than 10% of this population. Similarly, in upper sided bound, which is our real concern for this problem, is that 90% of the population is having value lower than the 10% of this population. So, our main concern is with respect to upper confidence bound. And for example, let's suppose that this x value is 95. Then it states that 95% of the one-sided bound. This indicates that 95% of the population is less than the x value, and the 5% of the bound is having value greater than this 95% population. So after understanding this clearly, let's get back to here and understand which ad is going to generate maximum revenue. Just by looking at the curves, you can make out that the ad number 5 is going to give the maximum revenue, as it is a left skewed curve, which means that most of the population is towards the left hand side. So which represents, if we draw the upper bound here, in everywhere it is going to give the normal population, but most of the population will be towards the left side of this graph. So we can tell that this is the ad which is going to give the highest revenue, because this is in demand. Now let's understand the working of upper confidence bound one more time in deep analysis. So what we have done is we have represented all the 5 ads in this plot. So after representing them, let's suppose initially all of them were having their median value at the center. So with the issue of time, with the passing of the time, their ads has been generated like this, some like this. So with the span of time, we have got the values of every ad, the clicks of each and every ad. So see here you can see it is the mode of the each of the distribution curve, and this represents the whole population, the number. These all are equally similar in the number of them. We can't make out which is the maximum. So after applying the upper confidence bound, for example, at a particular time this ad has been selected, then it will be reduced its population and move up, and its population will be shrinked down. Similarly, if for the next span of time, if this particular ad was selected, then it will also be selected and its population will be selected down. Finally, at the end of the time, we will get to have the most least, means the most shrinked value of the population will be at D5, which represents that it is having the highest upper bound. So most of its population lies below the upper bound value. So we can make out from here that at present ad D5 is making trend in the market. So we can suggest the ad agency that this is the ad which you should focus more now, because it is having a good amount of trend in the market and it is going to generate a lot of revenue for the company. Now let's understand it more clearly. Suppose we have D arms. For example, arms are the ads that we display to users each time they connect to a web page. And each time a user connects to this web page, that makes a round. At each round end, we choose one ad to display to the user. At each round end, ad I gives reward R of I of n, which belongs to set of 0 to 1, R of I n equal to 1 if the user clicked on the ad I, and 0 if the user didn't click. And similarly, our goal is to maximize the total reward we get out over many rounds. Now before jumping into the hands-on session, let's quickly have a look at the algorithm of Single Arm Bandit. The very first step is at each round n, we consider two numbers for each ad I, where n of I is the number of times the ad I was selected up to the round n, and R of I is the sum of rewards of the ad up to the round n. The next step is, from these two numbers we compute the average reward of the ad I up to the round n, which is given by Ri by Ni. Ri bar is the average reward. and the confidence interval is being calculated by this formula, and after that we select the ad I that has the maximum upper confidence bound, that is R bar plus delta I. Finally, now it's time for your favorite hands-on session on Bandit problem in Python. Bandit issue, let's import all the important libraries. See, it has been executed successfully. And now let's read the dataset and analyze what is there in this issue. So this is a dataset of 10 ads that are published in a web page by an ad agency, and it wants to know which ad is going to generate them more revenue. For that, they have given us 10,000 records, means 10,000 users whose activity has been displayed in this dataset, where 1 represents that the user has successfully clicked that ad and visited that ad, whereas 0 represents that he has ignored. So if randomly we want to make out which ad is going to be the maximum, or which is the ad that is generating the maximum revenue, if we just go on counting the values, then you see it is very difficult to make out, because every ad will have the same frequency, and when we visualize it, let me visualize the same through histogram so that you can understand it properly. See, every ad lies in the range of 1,800, 900 to 1,000. Within this range, it is difficult to make out that which ad is generating the most revenue, means which ad is it trending right now. So in order to understand that, what we have to do is we have to apply the upper confidence bound. The same thing which we have discussed in the earlier slides of algorithm, where we have to apply the formula of average reward and delta I, and upper bound is calculated as average reward plus delta I. And in order to use logarithmic function, we need to import math library. We have to import the math package. See, it has been executed successfully. Now let me just initialize all these variables, where n represents the number of records, number of users, and d represents number of ads selected. Initially no ad is selected by the user, so it is empty list. If the particular user selects that ad, then it goes on updating, and after that we are checking the number of selection into d and sum of the rewards into d. Then total reward is calculated, which will keeps on updating inside this for loop. So what we are doing inside this for loop, initially the maximum upper bound is 0 and ad selected is 0 for I in the range of 0 to d, means here d represents the number of ads. For each and every user, it is going to check for each and every ad. The number of selection is greater than 0, means if he is ready, means particular ad's value is 1, then the average reward is calculated and delta I is calculated and upper bound gets shifted. Else the upper bound initially, if nothing is there, then the upper bound initially is very high, and if our upper bound is greater than the maximum upper bound, which is nothing but 0, then we will update this maximum upper bound. We want to get the upper bound which is the maximum of the records, so we don't know which is the maximum value, so initially we will define the upper bound as the maximum value. So we have defined 10 to the power 400. So after that maximum, we will come to the confidence level, upper confidence level, just by updating its value. Whenever maximum upper bound is lesser than upper bound, maximum upper bound will be the upper bound, and that ad will be selected, and this particular ad will be appended to the ad selected list, and its number of selection rewards and sum of rewards and total rewards will be calculated as per the formula. So let me execute this chunk of code. This is simple algorithm repetition here, so I am explaining it little fast, and hopefully I think you are getting this everything. So I have executed it successfully. Now let's visualize the same plot, same data set. Now let's see the variation in the results. Now you can see how by calculating the upper confidence bound, we have come to a conclusion that ad number 4, which means in general from 1 to 10, it is ad number 5, because array index means here the index is starting from 0, so 4 means 4 plus 1, which is nothing but 5th ad is going to generate the lots of revenue, because its most of the population lies below the upper bound. And as usual, I have included code snippet for your fast revision, so you can pause your video right here and can take the screenshot of the same for your future reference. I hope this video proved fruitful to you and hope you have gained something extra than what you were doing earlier. Thank you.